What is time besides the smallest observable particle in which we delineate the forward progress of life? We will all die, and how much symmetry lies in between then is called time. We can split this up into days and years along the path of the sun, and this is the most commonly held tradition among all cultures in the world. We travel around the sun in a year, while every day the earth is rotating in these discrete increments of a day, or what we call a day. Even the clocks we have to tell time rotate themselves. Likewise, all objects with great mass tend to rotate as well. Newton described this type of behavior with his equation of gravity. In particular, gravity is inversely proportional to the square of the radius, and more generally that large objects tend to have more gravity. That we can imagine that as things entangle in a mass, there's a rotational velocity or acceleration that eventually will summon to the spherical objects we see in the world. Or perhaps that is one of the hardest things to imagine despite being immersed in the universe ourselves. In space, objects move as though it's somewhat like a vacuum, because they pretty much are in a vacuum, because there's not really much else out there except there's like planets and comets and suns and stuff, but that's far and few in between, right? Most of space, or what we call space, is empty. So it makes sense that as we travel, like as an analogy, it makes sense that as we travel over land, like a desert compared to a city, there's going to be less things to entangle ourselves with, just physically, just like there's going to be less developed areas, right? Like the only thing is like these tumbleweeds in the desert. Same for space and all the in-between. There's really no molecules or anything to contact with surfaces and to make other entanglements. So there's less stress being manifested from the stresses as compared to earthling life. So yeah, when you come back towards Earth in the sun, the time dilation will then become more apparent as though you were on the Earth. Time dilation itself is an effect of simultaneous occurrences or perspective, and just a fundamental part of the universe, basically how fast light can travel. And the dilation or simultaneity reveals the change in time in all directions theoretically in space. But we already know this, that we have to accelerate or produce a force to give us friction to move forward on the ground. And that causes us, of course, to move forward toward an object quicker. It's just so negligible, the change in time, or these time dilations. It's not until recently that it's been able to even be proven, right, that we have the instrumentation sensitive enough. Plus, the equations of gravity and motion tell us that we can accelerate space-time. It's just people want to live forever and go back to the Trump era. They want to return to the land of before. Everyone thinks in terms of physics of the impossible and not the interesting nuance of the possible. One being that time can be dilated in spatial dimensions, or that strain is us negotiating space-time stresses. So the Trump dilemma. What is the Trump dilemma? So there was a recent article describing the big simultaneous dilemma of our latest lives, the latest election and ensuing debacle. So the article came out in the Washington Post, and I want to talk about it in regards to time dilation and stress and strain, and then more so like revolving around a simultaneous idea or events or times. When looking at the Washington Post article describing the change of the follower count of popular accounts like Lynn Wood, Marjorie Taylor Greene, Sidney Powell, and Mike Lindell, the Washington Post article featured a graph of the follower account of each of the four, or was it five, and then the evolution of that number, of the follower number over time. So essentially what we saw was a stress over strain curve, or what we can understand as such, right? The people or the account of the individuals behave as materials that are deformed over time under a stress. And of course, the account fallings were not identical for each in absolute numbers like the amplitude, but nevertheless, there was a clear behavior that can be described metaphysically, but also in the fundamental ways we perceive the universe itself physically. So the basic understanding of strain and stress can be described using the curve, where for metals and other solid materials, we will see an elastic region of space and time, where the spatial coordinates or existence can be strained or deformed over time, and this deformation is elastic in that it is proportional to the stress. That deformation in time is proportional. That deformation in time is proportional to the applied stress is true in liquids as in solids as well, and that we know the resistance to the flow or deformation is the viscosity, where the viscosity is something we're all familiar with, right? That if honey itself will resist flow more than water, and something like ketchup, or even more so toothpaste, takes a certain amount of stress, like a press or a hit on the tube, for it to flow at all, right? So something like toothpaste will hang upside down and it won't flow outside from the tube. Likewise, we can model the behavior of the follower account of people like Lynn Wood, Mike Lindell, Marjorie Taylor Greene as somewhere between solids and liquids, as we might expect with people who are compromised of liquids and solids, because, well, at the end of the day, we are governed by the laws of nature. Right? So we may be able to update our trajectory or escape certain gravitational fields, but it comes with time or a strain because of the stress inherent. Suffice to say, we all eventually die. We don't remain forever in the universe as rational beings, but are reduced to smaller particles than before. The time we are moving, we live in a very relative world, one that we can describe, or at least compare analogously, as viscoelastic, that we ourselves, whether in real life as people or online, can behave with some viscoelasticity, as proven demonstrably through theory and empirical data, such in cases as this article and in general events and the general event in question, right? That the election and then the debacle after. So let's start with the most classic example of viscoelasticity. The classic example of a viscoelastic behavior, well, you can go look at it online. Professor Lewin, who I'm not sure if he came up with the experiment, but he was able to set up the different ways material or space can deform with time. So imagine you have a weight, and then the weight is attached to the roof by a string. And then on the bottom of that weight is another string of identical length and material. So there is a tension on the string on the top that it will be pulled down by the weight or the gravity of the weight, and thus will be applied over the cross section of the string, right? That although it may appear as a line in profile, a string is a woven material, either cloth, polymer, metal, and it will have an elastic period of deformation, which again is a function of time, and then it will experience a larger amount of strain with stress over time, and eventually, due to the material geometric boundaries and time constraints, there may be a failure structurally, and the weight will fall. If we pull on the bottom string, though, within a short time frame and a lot of force, so a relatively large acceleration, we will tear the string on the bottom while the top string remains. That's because the top is being strained at a constant acceleration of 9.8 meters per second squared, the gravitational pull, a much smaller one compared to whatever you do to tear it down. So while the tugging causes a huge change in the velocity of the material on the bottom, it doesn't allow for the elastic period of the top to come to full relaxation, and then it will be structurally weak enough to break under the weight of the object below it. So we understand this as time dilation in space-time. This behavior can be exhibited in many other examples and has to do with general time dilation in the spatial directions, or better put, strains in space-time. That material exists in space and time, and this can be strained over time through applied stress and in combination with internal stresses as well. A stress is a force over area, and a force, of course, is mass times acceleration. A more pertinent or fundamental question is, what is the change in time over spatial directions? Or how does time change when we displace in the y direction? How does time change when we displace in the x direction? In a perfect world, we would just translate through space in a straight line, and if we were to change direction, we need an acceleration or a strain in space-time. When we want to walk, we tear our legs apart, and they compress in a sinusoidal wave as well, and you translate forward in time through a force. And of course, again, force is proportional to the friction constant, and force is mass times acceleration. So we accelerate from rest and go forward in time and space. And we can write this down as a near and perfect translation across the plane when we walk on the ground. Of course, on small enough wavelengths or time periods, it appears so. Things are a little more complicated, though, and viscoelastic. So imagine we have a chair on the carpet, a brand new thick carpet, and a heavy chair. It will take time, and if we give it time, it will sink into the carpet. That's like the top wire of the classic example of viscoelasticity. The chair sinks into the carpet, and if we want to move it, we can drag it fast, which will cause it to become more like our hand or like us, or we can drag it. And if we take it fast, if we drag it fast or grab it, basically pick it up, the movement will be jerky with juts and jumps. It will be very herky-jerky, right? Conversely, if we drag it slowly, it can translate across space and time as a particle on a plane. If we think about the material or mass the chair flows over, that being the carpet, well, the carpet fiber is stress, and then it's twisted together, and then it's probably entangled in secondary knots, and then we put our chair on top of that. So the relaxation of the chair into the material of the carpet is probably 3 or 4 layers of enfolding entanglement deep. So we can see how space and time are intimately linked in rotation. If we allow for a constant v or velocity over the top of the carpet, we can translate as in a vacuum. But what really happens is there is rotational movements or strain from the carpet and in the carpet. Essentially that we don't walk on water or slide the chair legs perfectly over the top of the carpet. It's a bit of both. And again, if we just yank the chair, essentially, it will become a part of us, and then its travel through space and time will be more like us and not traveling through the carpet if dragged slowly. Ultimately, both can end at the same stage. One might be worse for the weary as you pull your back lifting a table instead of putting something underneath the legs of the chair and then dragging it slowly over the carpet. Again, the time is dilated in all 3 directions differently, depending on mass and acceleration, but surface area as well if considering pressure, because stress or like a shear stress, torsion stress, rotational stress, all in all, we can see that the change in T over change in space will change. We can imagine the more rigid a material due to processing would be like if you had a sore back, so you don't want to tug the chair or table, but want to get out a dolly or forklift, or you want to hire a mover, so you don't have to do any strain with the same stress. You learned from the last deformation, and now you can say you won't stress as much as the last time because you have more memory with the stress, right? You're less elastic. With an elastic material, we can imagine that it's less rigid and thus can drag a chair over the carpet like last time. There's less memory or more athleticism and youth in some cases. Like a young person doesn't have to warm up or stretch to be linger because they're young, right? And then whereas somebody who might stretch if they're older because last time they came out they pulled their muscle, right? So they have a little more memory. So moving on. Time dilation. The card example. One way we can simply think about this is that if we have a card, like a playing card or a postcard or something, and it's balanced on top of another card, and from these two cards is stacked another card on a table in front of it. So you have a stack of 2 cards, one on top of the other, and then in front of that is 1 card, and there's no stack. So the same table that the stack is standing on, we want to transfer the top card of the stack to the same state as the one it is already on to the card in front of it. So basically we want to move the card from one on top of one card to the other, but we're going to do it like a human. So we could tear it, and if we tear it enough and take one end, much like one leg goes forward in a human, we'll do that with the card. So one end or half of the split will go forward until we imagine that one half is balanced on one card and the other leg or the back leg is balanced on the original one. So it's a state of limbo or in between. This would be the in-between state, and of note, because we can then see the rotational aspect to time, or its dilated effects in space. That the farther the time is, the more of an angle of an angle that we make when we tear the card, or the more it is dilated over space. That is a moment of elasticity, or maybe better said, an electronic state. Say if we're standing on a ledge that is giving way. There's a timing issue where we have to jump to get to the other ledge because we can't go back in time, basically. The constraints are so that eventually we want to jump to the ledge on the other side over a gorge, and we have to time it and move through the space in an appropriate manner as to arrive at the right moment on the other side. That in between us where the leg is on the one ledge and the back leg on the other. and likewise the card. So, but the card in front, or you can imagine the ledge behind us is giving way, right? Or you want to move the card from one stack to the other, but the card in front of it is moving, right? So there's a time constraint. So the card keeps tearing until there's no return, right? That eventually the distance between two cards is going to be longer than the length, so you'll tear the card in half, right? Its elastic period is over. But the card has a physical length L in space-time, so like the weight in the classic viscoelastic example that is held up by a string, there's time constraints. So if we have memory and understand the time constraints, we can become more rigid in nature as a collective being or society. We can imagine that the moment we have one leg on both ledges and they are equidistant is a moment of symmetry and simultaneity. Each leg is no different than the other if both at rest and can have their own clock. That is, but if you move the back leg towards the front, the back clock will not perfectly align with the front clock, and that's what we know as this kind of time dilation. But we know that if you accelerate toward a light or a clock, you will see it quicker than if not, right? So that's nothing earth-shattering. It's just the sensitivity in instrumentation or instruments has come to a state that we can measure nanosecond differences in time. So time dilation, elastic regions. Imagine that card from the previous example is now is an elastic band cut in half. So it's an elastic string. If we do the same thing as before, we can imagine the string would be elastic up to a point. So you would have one end of the string on the back ledge as it moves away from moves away towards the ledge in front, and you move forward. And as you move forward, it repeats, but the band doesn't rip as easily as the card. There is a difference in the very fabric or nature of space-time that the card itself will rip or tear quicker than the elastic band, right? That the paper itself has a different type of material property. Or that the memory or age it has, the more age it has, the less farther it can split or jump. Essentially, less athletic you become. Right, and more memory you will need in sports, right, to hang with the more agile and younger players. That's why we say veterans sometimes they don't have some of these tangible things, but they have more of the intangibles, like they have more leadership abilities, right? And that's why you keep them around on the team because they're still good players, but they're just not quite as young and agile, so that you need other things that they can contribute. We can see this would lead to a more mobile and flexible particle, one that would have a large elastic ability to take stress and turn it into strain proportionally. Or you can imagine lose a follower for every one they gain, whereas a more brittle material like steel would be reluctant to change with stress and have a more destructive end. Again, there's an angular momentum or symmetry to nature. Of course, that a planet and the sun appear as spheres, and the gravity forces are what make this kind of perfect circular shape or radial symmetry. Much like the tearing of the part of the leg produces a rotation, an angle when we walk, right? We move our leg forward and it makes an angle. So does gravity for large masses. Moving on to projectiles. Time dilation, projectiles. For a ball dropping from the highest part of the Earth's atmosphere to the ground, there will be a time dilation in both directions. Consider a ball at constant velocity in the x direction with initial velocity v0 x, and it is then introduced into a field of gravity. For the ball with no acceleration in the x direction, or for a ball with no acceleration in the x direction, or just constant velocity in the x direction, the displacement is a matter of time only in the x direction. For the ball accelerating in the negative y direction, the displacement is dependent on time squared, or a plane of time, which can be aligned with the x and y direction the ball travels in component form. We see that for this simple problem that the time in the x direction varies with displacement in the y direction at an angle, and the tangent of this angle we can call gamma. So gamma divided by the initial velocity in the x direction is equal to the change in time in the x direction with respect to displacement in the y direction. So how does time change in the x direction as we displace in the y direction? How does time dilate in the x direction with changes in the y direction? dtx over dy. As the angle of the tangent increases, so does gamma, and in turn the change in time dilation, or delta tx over delta y. We can imagine that as we pull on strings in other entanglements, there is a velocity and time component. As change in velocity increases, there is a smaller time dilation, which should make sense in that you traverse the same space in less time. We can imagine if we have a small change in y and a big change in tx, this is a long turning motion or a long pull. The angle or slope is big, or transversely, the velocity could be large enough to start overflowing bounds or have structural failures in a machine or system. A large change in y with a small change in tx would mean a small angular sweep at a fast rate. You try to pull your way out of a thorn bush while entangled and ensnared. A lot of particles will be made with all the bits of you in the bush, and then also the bits of the bush removed from the larger mass. Small time dilations will add up. We can point to each scar and cut in our body, and then we can go back to the thorn bush and see the damage we left as well. The time dilation in space will appear as the strain. Of course, this time in the direction will strain in the y direction. Of course, the time in the y direction will also strain in the y direction as well. Displacement as proportional to 1 over v naught x. So it's inversely proportional to the velocity. And this is expected since there's no acceleration in the x direction. And that velocity, well, velocity is, that the change in x over change in t is velocity. So if change in x is just v naught t and there's no acceleration, if we just divide change in x by t, we get velocity, right? And then we can imagine that 1 over velocity is the inverse of that. So this is given as much as the other, but it's not quite as accepted, right? We accept that velocity is x over t, but do we accept that t over x is 1 over velocity? We only accept that time dilates in the x direction with changes in the y because of our ability to measure the difference and not notice the dilation. That from these rotational symmetries and other wave-like behavior at small scales or large scales with significant or sufficient surface area, that we are able to kind of see these mechanical these machinations of the universe, right, that we don't see on these small scales, and then we can make analogies. The change in time in the y direction with the displacements is much the same that it is dependent on the velocity in the x direction inversely. So small changes in velocity are like times we see the drawing of the material under the weight of the gravity. That the deformation is in the y direction, and if we add more force, we can see additional strain in time. We then reach the limits of the integrity of the material itself sooner, and this happens in the radial direction and not the axial one. For example, we don't rip the tip off a material during a tensile stress to failure, but the middle rips in half, or it fails in the radial direction in the middle. There will be nucleation sites or holes in the middle of the beam when it's about to fail, and then eventually these holes end up meeting the outside, which itself is concaving in or necking. If we have high velocity changes, we tear the material, or that we don't dilate the time as much because the material will fail. There's a time field, and if we have a perfect line of Tx and Ty, then we can say that there is no time dilation and perfect simultaneity. But that, of course, isn't true. That we'll never have perfect simultaneous events. Now, going back to the chair over the carpet in the original article. Time dilation, chairs, and entanglement. We can assume that Lynn Wood acts like dragging a chair over a tile, while someone like Mike Lindell a thick carpet. But all of them eventually have to drag the chair over a bunch of rocks, which we know as the non-elastic period. So we can imagine there is a degree of elasticity in the movement in the material, but also of viscosity in that if we apply a force at very small incremental loadings, we can just accelerate the mass or apply a force at the limit, and it strains elastically for some time. Or there is these non-relaxational translations that are repeatable. Like in our lives, a lot of it is the same, but it's the differences, most of which we can't quantify, that stir things up. That all those torsional and twisting entanglements, 2 or 3 layers deep, are like dragging a chair across a carpet, and that time dilation of Tx over y is dependent on the tangent of the angle as well as the velocity. So we can see that this is an embedded entanglement of an angular velocity and translational velocity. That tangent theta has an impact on the time dilation, or how much strain is measured as velocity. We can imagine that dragging a chair over a completely flat tile or forklifting over a warehouse floor is preferable to dragging across the carpet. Anyone who has moved a table or chair over a carpet will notice that the rocking and entanglements might loosen screws in the table or chair if dragged hard enough, right? There's enough vibrations going off that the chairs, the legs on the chairs might, or the table might loosen up. Someone like Lynn Wood had people with little entanglements with others, and he presented this flat surface or rigid cold material that very little time dilation occurs in with high stress. We know this because he gained a considerable number of followers in a short period of time, linearly too, for a good part of a week or two, eventually reaching the yield strength, necking, and then ultimately the ultimate strength and failure. We could imagine at yield strength, all the materials are like dragging over chairs over rocks, that the strain in the chair will be evident, permanent, and potentially destructive to the point of failure, that the strain increases dramatically as compared to the elastic phases. When looking at the temperature effects of the stress-strain relationship, we see that as the temperature increases, materials have elastic periods that are shorter and smaller in amplitude, or they have smaller yield strengths and produce a lot more strength compared to a cold work material, which makes sense. That many materials see more ductility in their more energized or heated states because the molecules have more energy to move around, and the secondary structural entanglements don't stop the primary entanglement deformations and permanent strains anymore. No matter how smooth you try to draw it out, drag a desk or chair over rocks like big ones, they will get permanent damages. But if we added the secondary entanglements like grass and more surface area like dirt instead of rocks, we get more realistic or familiar space-time constraints than if we just drag and then we can just drag the desk along the grass and the ground along like a carpet, right? And there will be little damage. There's also a solid and semi-solid state systems like oil and gels that are in phases of their own. Like if you cook and you save the stock, you may form a gelatin with, and then that's going to have this organic fat that gels up as well on top of it. And then there's going to be solids on the bottom of the pan. And then all these will exhibit different behaviors. For example, the fat can be melted easily and separated easily. And then the gelatin a little harder. And then the solid will be the hardest and require shearing from scrubbing and heat. And then you might have to add like soap or something. The heat gives more rotational energy to the molecules in these states. And then they are able to move or unfold or disentangle, behaving more like a liquid than solid gel. The solid fat melts easiest because of the long chains of fat. The same reason an egg cooks or firms up quickly is because of the long chains or the heavy molecular weight. Lots of folding in secondary and tertiary structures that don't really have strong bonds compared to something like a metal or steel, which is very rigid and held in with a crystalline structure and doesn't fold over itself. It's arrayed in a crystalline structure. All in all, the people in the article and graph displayed a shear thinning behavior that as though they were worked or stressed, they began to thin, or that as more stress was applied, we saw the resultant strain increases. Like cement is hard at first, and then every turn mixes a lot, but at some point you're just turning it over and over, and then it doesn't really mix anymore, right? It doesn't get any thinner cement. It just kind of goes in a circle. And then things like paint don't become thinner, right? At first they're not mixed, and then we mix them, and then they become thinner, but then they don't become any thinner with increasing stress. They reach a point of well mixing, and then we coat the wall with it, basically. And, of course, on the opposite end is shear thickening is like egg whites or whipped cream, which has to do with the strains. I think it becomes, you have proteins and stuff that become more entangled, or the larger structure stays intact and the resultant material. We can imagine that Lynn Wood was someone disconnected from the state as to attract a separate fan base that would be willing to leave Twitter just for him. But at the same time, he might have just benefited from being booted from Twitter first. But that could just be a materialistic property of himself, that since he's crazier, he's going to get booted from Twitter first and thus have this huge he'll have the elastic period, but the elastic period would be more rigid, with a slope on it will be larger. And then we can say that Lin Wood promised the most outrageous lies. Like, he was able to give the ones who were the most resistant to the stress of reality that they wouldn't break. He was able to give these lies to the followers who were most resistant to the stress of reality, that they wouldn't break basically or strain with these high instances of stress, as opposed to somebody who followed Mike Lindell. Right now, as many people followed Mike Lindell, and then we saw more stress or more strain at lower stress or lower follower accounts, which seems to show that he had a more elastic or less rigid behavior. The people that follow Lin Wood behaved like steel, or that his informational black hole or gravitational pull is very strong compared to someone like Mike Lindell. Although you could argue that they both are crazy. I mean, they all are. It's Mike Lindell who's the most legit out of all of them, with an actual company, and people who follow him are more normal, right? That he has these kind of secondary and tertiary structures that entangle with the system that is stressing him. So he can't, the people he wants to pull away are still on Twitter, or they're like normie people, or that he can't go crazy because what is he going to do with his company? He's just going to lose his company over a lie? No, he's entangled. But eventually that lie, or the 2 weeks that they keep promising every other 2 weeks, catches up, because the equation is pressure equals force over area, and the force, of course, equals ma, which is, and then if we want to rewrite ma, or that we know that using a kinematic equation, acceleration is change in x, or length, over time squared, right? That the units of acceleration are meters per second squared. So as the position changes, we see a doubling in the time in the inverse direction. So if change in x is a strain, which in the case of the Washington Post article in the graph is time. So if the strain is 2 more weeks, but then the stress is that every 2 weeks, 4 weeks are taken off, right? That you see that you have this kind of closing tunnel, right? That if you say 2 years from now, or the election, whenever the election is, every 2 weeks from then, 4 weeks are erased, right? That you come in, that you have two ends. On one end, you come in 4 weeks every 2 weeks. On the other end, every 2 weeks you go forward. You can imagine that the other end, for where every 4 weeks it comes in, is going to close quicker, and you're going to be in this tunnel that collapses on you. Or it's like a man who's tied up and there's a bomb ticking away next to him, and you have to untie yourself before the bomb ticks. But you're not going to be able to do that in some of these situations. So we can say the overall goal of all these foolish plans is to build a time machine, to go back in time to when Trump was president, or the night of, at least, where they felt the last correct timeline was intact. For a while, Trump was president, even though there were doubts and impeachments. But for every day for 4 years, you could bet on it that he was in fact president. But all of a sudden, for these people, the bedrock of their truth was gone. No more real news or solid earth to revolve around. So they tried to build a time machine with extravagant lies. Trump will be instated in 24 hours. This is the same type of lies that we saw with Ukraine will be taken in a day. The same type of short-lived ghetto superstar behavior. $5 spent to buy 1 gallon of Supreme gas for a BMW with 200,000 miles when you live in an urban dump. Behavior that can lead to total structure and destructive failure. Nonetheless, it is an untangled thinking that steel or other materials are more planar or plane-like and allow for mobility at least electromotility. They allow these meta-states and allied states. That is due to the readily available valence electrons. But they exist in a relatively disentangled structure, right? The metal, which is crystalline, and it's very rigid. It's not folded, it's not entangled, it's not random, it's not flowing. It's very rigid and crystalline and repetitive. Again, they are rigid and planar facing against the news. And you can imagine steel can be stressed and still be strained, but it's going to strain less for the most part relative to more elastic materials. That is because its bonding, the crystal structure, gives it the very tough behavior, and this is also, we see it in the radial, axial, and diagonal properties. We see when stressed and strained, and the strain results. A metal can blunt, but it also can cut through something like butter, and that's depending on its shape and its rotation. But this shape, or the ability to be shaped into these kind of sharp points, is a product of our property of the material itself. That it can be, that we can get these planes or sheets of atoms right, to be very flat surfaces. We also know that metals, or the molecules in metals, can vibrate, and they're ordered in crystalline or symmetrical repeating patterns. And then when we give them an oscillation, these can produce sounds like humming across various frequencies. A metal like silver can be polished as a nearly optical mirror. So whatever news comes in will bounce off mirrored. Someone like Mike Lindell was entangled himself with Trump, but also like stores like Target for My Pillows, and then also the company Fox News, where he advertises for My Pillows. That he's a more legitimate person, and that there are degrees of fan bases for him. Weird as that is to say, that he behaved most like a polymer that would have some elasticity, but ultimately strain and fail. And of course, the strength of his followers is weird, considering he is kooky. But it said it came much later on, right? That he at first was somewhat normie, and then he became more crazier as it went on. And that Lin Wood really struck while the iron was hot, right? I don't even remember what he said, but he said basically like Patriots are in control. I mean, that Trump is like in the White House right now. Biden is like in Guantanamo Bay. I mean, these are the levels of lies these people tell. And that he really struck when the iron was hot in that elastic phase. And he gave the craziest timeline for Trump, or for the return to the Trumpian age. And I think what's most probably interesting is that a star produces iron through fusion before it goes supernova and explodes, producing the higher atomic weight metals like gold and silver that exist in the universe today. And that's what we saw today, right? Or saw in someone like Lin Wood, he's like more like iron or steel or something, right? A car is metal mostly, or where structural integrity is needed to absorb the stress, and have not the material not strain. You want the material to be metal in a car, right? Like, so your engine or the chassis, whereas other materials on the car are more viscoelastic, right? So your tires are rubber. And they're very they're like a polymer, and they rely less on crystalline structures and more on entanglements in these large chains and foldings to propel you forward and then wear over time at a more economical and taxing way, right? A shopping cart is fine until a rubber wheel gets stuck with entanglements of hair and other crap on the ground, and then the cart won't move as well. But then on the other side, if the cart has a hole in it, or it's made of like butter or plastic or something like that, just gives away, and every time you put something heavy in it, it starts to bend. It won't be good as a cart, right? That you won't be able to hold goods as well.